Okay, this is lecture 2 for waves. We will talk about Doppler's effect. But before we talk about Doppler's effect, the primary observation of Doppler's effect is in sound wave. So I kind of want to recap what sound wave is first with you. And here there is a speaker that is already in slow motion, and you can see the membrane of the speaker kind of vibrating. Okay, so this vibration is the reason why you have sound wave in the first place. It creates a variation in pressure. So all this GIF I will include in the links in the description. So here you can see the speaker cone moving like this, and as it moves, right, it disturbs the air particles, and the air particles kind of move and transfer energy to their neighbors. So if you look at it, right, wow, it looks like the wave is moving with regions of compression and rarefaction, as mentioned in the previous lecture. So these GIFs are all from Flipping Physics. Pretty good channel. All right. So links are down below. So if you look at one single layer or particle, right, that blue layer, it is actually not moving, it's just oscillating left, oscillating right, oscillating left, oscillating right. Okay, this is an important concept. And again, longitudinal wave, okay? So parallel. So because of this, we have places where the pressure is high and places where the pressure is low. So we're going to represent this by drawing a red line at the crest of your sinusoidal wavefront. Okay, the sinusoidal wavefront is just to show the changes in pressure. So you can see, if let's say we know sound travels in all direction, 3D, okay, so let's say now you look at the particular tuning fork, the sound is traveling outwards. And if we draw a red line at the crest, you'll be able to see that, wow, it's like the red line traveling outwards, no? And these are all concentric circles, okay? And here is where I purposely leave a few minutes so that you can stare at the GIF. Isn't it very soothing? Can meditate now. Okay, so if you look at it again, the red line is where all the particles are together. This is where the high pressure is. Okay, so this is your sound wave. So we are going to draw these concentric circles. Concentric means they have the same center. Okay, to represent sound wave in different situations. So we're going to start off with a car, but we're going to make it a bit not so straightforward. The car will have a horn that he or she will be pressed as the car travels from left to right. Okay, so the car is going to travel, from here to here. Yeah, flip camera problem. So there's the horn, or the so-called sound wave. Okay, there's the center of where the wave will originate from. Let's look. One circle, two circle, three circle. So at first glance, it seems like there are some ellipses here, but actually they are not. They are all circles. But now they are not concentric. They don't have the same center because the center keeps moving, the car keeps moving, but they are all circles. Okay, so if you check out the blue one as reference, you will notice that as the car travels in this direction, right, it kind of squishes or compresses the wave together, okay, or the variation of high pressure together, okay, and at the other end, it drags out that pressure, the wave front. So you can see as it travels on one side, the wave is squished together. So if let's say I'm standing and the car is driving towards me, okay, the sound source is moving towards the observer. I am the observer, the car horn is the sound source. So I will be able to observe that the crests right now drawing to represent, crests are closer to each other here. If the crest is closer, this means that the wavelength is less. Okay, if the wavelength is less, because the speed of sound is constant, then the frequency you hear is higher. You will hear a higher pitch. Okay, and okay, once again, I'm replaying the video a bit. So you can see where the car is approaching the observer, the wave fronts are closer. And because the wave front is closer, we can consider that the frequency will decrease. Okay, V constant. If lambda decrease, F must increase. Okay, so that observed frequency is the one that increases because the wave coming towards him is being squished. So he observes and hears an increase in frequency. Or he just gets more sound wave per second. You just look at it. If he stands at the back of the car, he gets less sound wave per second. Less sound wave per second. The crests are further apart. Frequency will drop. Less sound wave reaches him per second. Okay? So don't worry about it too much. Right now, if you turn on your mic, you can hear frequency increase.
Of two different viewpoints during the demonstration.
This is
on the left, you see me in the car, and on the right, you see the event from the perspective of the stationary observer. Before we heard what was happening from the perspective of the stationary observer. Now let's listen to what we hear from inside the car.
Hear the changes in frequency. Let's see. Oh wow, it's as if there is no change. Try that again.
The frequency and therefore the pitch you hear is constant.
Okay, so that's an important idea here when we define. Doppler effects rely on relative motion. Okay, so when we define, right, we say that this is the change in apparent frequency or observed frequency due to relative motion. So it has to be either moving like this, so this is the observer, this is the source, or moving like this. Move like this, no relative velocity. Okay, due to relative motion between the source and the observer. So source and observer, there have to be some form of relative motion. If you don't understand what relative motion is, you can talk to me. Normally, this definition is 2 marks. 1 mark is when you say there's a change in observed frequency of the wave. You can specify the wave to the question if needed. Okay, due to relative motion between the source and the observer. Okay, so I'm just giving you a drawing to visualize the video that you watched just now. Okay, so in the diagram, the first diagram, you have a stationary source. And let's say now we're going to draw some observers. Nice or not, my stick figures. So observer 1 on one side, observer 2 on the other side. Okay, and we're going to assume that the frequency of the source of the siren, so now instead of using a car horn, I'm using a ambulance. I'm also going to roughly draw out or trace out the wavefront for you. Okay, so you can see the wavefront doesn't change. So the frequency observed by observer 1, FO1, and observer 2, FO2, and the source frequency Fs should stay the same. So I'll write that down. Fs will be equal to FO1 and is equal to FO2. And this is due to the fact that there is no relative motion between the source and the observer. Okay, they're just standing by the road. The ambulance is just parked there. No one is moving. Let's look at the second case when the ambulance moves forward with the speed of Vs and the frequency of the source is still Fs. The siren is Fs. I'm going to plug 2 of my observers in once again, observer 1 and observer 2, respectively. And in this case, what you will see is on one side, because the ambulance is approaching observer 2, that the wave profile is actually squished together. The wave is closer to each other. Okay? And for observer 1, where the ambulance is running away from, wow, the wave is stretched longer. Okay? So once again, you cannot see the sound wave. What you can hear is a change in pressure in your ear. Okay? So observer 1 will have a drop in frequency. Observer 2, a rise in frequency. But how to prove that? Well, the proof will come soon, okay? But I'm just going to write down what I see for the wavelength. So for observer 1, let's say we call that wavelength lambda 1, and observer 2 lambda 2. Lambda 1 will be longer than the initial lambda, and lambda 2 is shorter than the initial lambda. Okay? I think I wrote wrongly. Please change the sign. Okay, lambda 2 is less than lambda. I wrote wrongly already. I can't change now. Okay, so right now, what we're going to do is we're going to try to come up with a relationship or a derivation of the observed frequency. So we're going to start off with the stationary source first. We know that for the stationary source, in the time t is equal to period, the distance traveled by the sound wave is equal to lambda. The proof was in part 1, okay? Or the idea of it lah. In period t, one complete cycle, the wave will travel by 1 lambda. So right now, what we will do is we will plug this into the equation of distance is equal to speed multiplied by time, since the velocity or the speed of the wave is constant. So I'll get distance, which is lambda, will be equal to the speed of sound wave multiplied by the period. Okay, so if the distance is lambda, then the time would be period. I'm just going to label out v. This is the speed of sound, which by the way is not always constant, okay? There are different values for speed of sound. Please try and go and, I don't know, read the question, okay? Don't memorize. Huh? So what about the case of the ambulance moving? So in the first case, you have the observer, for observer 1, the source is moving away. Okay, if the source is moving away, then what we can say is the wavelength or the wave stretches. So the wavelength is longer. And because it's longer, right, we already know that the relative speed actually stretches it out. So instead of just traveling v times t, it will be v plus vs times t. Okay, so that is lambda 1. Lambda 1 is bigger, so must be plus law. Okay, and then let's consider observer 2. For observer 2, the source is moving towards this side. Yeah, source is moving towards. Now, when the source is moving towards, the wave is being compressed, it's being squished. I say in inverted comma because these are not terms that you can use in your explanation. Alright, so we are going to use minus Vs instead because the length is shorter. So minus law. You compare to the original length. Alright, so number 4. Now we're going to have to put all these equations together. But I'm just going to start with a familiar equation that you have. Since we know that speed of sound is constant, when I say constant means sometimes it's 340, sometimes it's 330, depending on the question. This is what I mean by a different constant. But we can treat it as constant in this scenario lah. Okay? So let's say observer 1 observes a frequency FO1 and observer 2 observes a frequency FO2. So which means V will be FO1 times lambda 1. Let's say we take observer 1 first lah. Okay. So I have a value for lambda 1 in number 2. So I'm going to substitute that in. Okay, substitute equation 1 in. And then what I would do is I will move or put all the velocities together to see a ratio, because I like ratios. It's my best friend. So FO1. And this T is just 1 over F of the source. Remember? This was the original one. 1 over F. Okay, so this T is the period of the source. Okay, and if you are a bit like not sure, you can always label all of this as TS, not Elliot lah, just TS. Alright, so what do we have now? I'm just gonna write them together in the same fraction. Okay, so you can see right from this equation that the ratio of observed to source frequency is equal to the ratio of observer is not moving, so the relative velocity of the observer and the relative velocity of the source. But observer is not moving, so you can just take that. The blue one is often used in your mark scheme because it is given. Good news! Equation is given in your second page of your question paper. Now we're going to move on to look at observer 2. Okay, we're going to repeat the same process again by substituting FO2 with lambda 2, so V minus Vs times Ts. We'll repeat the whole process again, bring all the V's together. Okay, and as you can see, I have made a mistake which I will rectify in a few seconds, don't worry about it. So FO2 over TFS, because TS is 1 over Fs. Okay, so again, we just did for FO1, now we're going to do for FO2. I have corrected the mistake. Yay. So we're going to draw a box around this. Okay. And from here, you can already tell that if we combine both equations, I will get the ratio of observed over source is V over V plus minus Vs. Now, if you ask me, I think the last equation is the one that you should know how to use lah. The main idea is just you must know how or when to use the plus and minus sign. So for example, the V, I'm just going to label all the values, all the unknown there. So capital V is, V is speed of sound, Vs is source, Fs is frequency source or source frequency, and Fo is observed frequency. Now when to use plus, I'm back. Alright, so I have to go away so you can see the notes. Anyway, the whole idea here is if the ambulance is running away from you, your frequency is lower. The ambulance is headed towards you, you being you, the observer, the frequency is higher. Just imagine the wave being squished together. I find that quite helpful. And that will help you decide when to use plus and minus by looking at the denominator. If you want the denominator to be big, then the frequency observed is small. Denominator small, frequency observed is big. Okay, so it just depends on the ratio lah. Okay, so right now I want to talk a little bit more about Doppler effect, but Doppler effect in light. You might think that Doppler effect is mainly on sound, but the only reason why we use sound is because we can observe sound. I cannot show you this, that your eyes cannot see the shift. But let's say, for example, we imagine a star. So look at my cute little 5-year-old star. Okay, and the star is moving towards your left. Okay, and there are obviously two observers, little tiny human men there. Okay, now what happens when the star is going away from you? The wave gets star or sun gets stretched out. So the observer 2, and you have observer 1 there. The observer 2 obviously gets less wave per unit time because the waves are stretched out. Okay, so if there's less wave per unit time, because the sun is moving away from the observer, I'm just going to write them down. The sun can be replaced by star or any object in the universe that gives you light. Okay, so let's say the sun is moving away, or the universe is expanding. You know, we have this theory called the Big Bang theory where the universe is expanding. Okay, so let's say the sun is moving away from observer 2. So obviously your lambda is longer. Lambda increases. And if your lambda is longer, right, what we have now is that your frequency is less. Now the frequency is less. This means, right, we shift into the red color. No, sorry, not shift into red color. Any drop in frequency we call red shift. Doesn't mean you can see red. It just means that the frequency decrease because red has smaller frequency or lower frequency. Okay? So actually we can measure this red shift. That's why we have a theory that the universe is expanding. Okay? Now what happens if, let's say, there's an observer 1 on the other side? Actually, I would ask then, who is this observer? Is it God? Is it an alien outside of the universe? Are we like ants in an ant farm? Who knows anymore? Insert existential crisis, but never mind. Let's assume that the sun is approaching or the star is approaching the man. Ding ding. Observer 1. So the opposite will happen, right? Lambda is squished together. Observer 1 gets more wave per unit time. So the frequency increase. So we call this blue shift. You might be asking me, why isn't it violet shift? I don't know. They name it red and blue. Increase in frequency means you move into the blue spectrum. Okay, so this sun moving away and universe expanding thing, I will include another video in the description box down below. You can watch it if you're interested to see how we use a red shift and blue shift to come up with the theory that the universe is expanding. So that's it from me. I'll see you on the example video. Bye bye.